I know.
I know.
All right.
I'd be upset. I was like,
Let's jump right in.
my accounting skills are low coming in use, bro. I thought I didn't learn anything in accounting, but I look did learn quite a bit in accounting.
Christmas break.
Bro, I don't think I'm working too bad. I have a lot of practice with that stuff.
Remember your indicators.
Yeah, that's all I need to do.
Because
Because
you're chilling.
yeah, Model UN helped me so much with all that stuff. Yeah, prep time is insane.
Right over and presenting.
I feel like you need to work on speed, because I mean, you only have, what, 10 minutes?
And present for 10.
Yeah.
So I feel like Big Ryan Robin, because she's the church.
Okay. Tell your neighbor what you think. Tell them why you think it. Correct answer is A. What I am looking for is not, hey, look, it's coasting at a constant velocity. That is the symptom. That is the consequence of the condition for momentum to be conserved, and that is if there are no external unbalanced forces. There are no unbalanced external forces. Okay, so you have gravity, normal force. Okay, are these external or internal forces? If your puck is the system, then normal force is from the ice, which is not part of the system, external force. Gravity is from what object? Earth. Is that part of the system? Not part of the system. So both of these are external forces. However, they're canceling each other out. They're balanced. Okay? So we can say there are no unbalanced external forces acting on the hockey puck. Therefore, momentum is conserved. And the consequence of that is it continues to move at a constant velocity. Good with that? Okay. So neighbor, tell them why. Correct answer is B. You have an external force that is unbalanced from the collision. Same scenario. Let's put both players in the system. Tell your neighbor. And everybody okay? This is just like the bowling ball, bowling pin example. Okay. So all of a sudden we took the same scenario and we looked at it in such a way that momentum is still is conserved. If we put both, okay, so prior to this, the force from the collision was an external force that was unbalanced. But if we incorporate the object that caused that force into that system, then we make that an internal force. that. So it's really important to know what's part of the system and what is not. Here, with that. Correct answer is?
B.
Correct answer is B. Skates provide an external force of friction, not part of the system. Nope. Thumbs up. Thumbs down. Yes, it is. No, it is not. Okay. If you took the stick and you slid it across the ice and it hit the puck, and you put the puck and the stick in the system, then momentum is conserved. In this scenario, were there any? Okay, so I'm good with the fact that the force of impact between the stick and the puck is an internal force. But are there any other external forces that are not balanced that are acting on either of the objects?
You apply force from the player onto the stick.
Yes.
And the stick applying force to the move, transferring the force or kinetic energy to the puck.
So that's internal. We're good with that. But this force here, you are not part of the system. You are exerting an external force on the stick. Does that make sense? So just because the objects experience an internal force between themselves, if there's any other external forces acting on objects in the system, even if it's just one of them, momentum is not conserved. You okay with that? Got your neighbor? Correct answer is
B.
2 votes for B. Not conserved. Correct. Gravity is an external force. It's a conservative force from a work energy standpoint of view, but this is a totally different ballgame. Okay? It's a different scenario. Gravity will be an external force. It's in free fall. It's speeding up. Momentum is increasing as it falls. You good with that? Now, same scenario. Let's incorporate the Earth as part of the system. Is momentum conserved? Okay. Yes, it is conserved. Gravity is now an internal force. This is true conceptually, but in practice, if you ever have to like incorporate the Earth as part of the system and do math to like prove your point, abort. Like you never want to like figure out how much the Earth moves due to the puck dropping. Like that's just stupid. Okay? Like if you find yourself, man, I need to incorporate the Earth for momentum to be conserved, then do something different, another strategy. Do like force times time is equal to change in momentum. And that will be that would be the route you would want to go. You all right with that? Yep. All right. So, this is a subtle but important point. Momentum is a vector, has direction. If momentum of the system is conserved, then the direction of momentum has to be the same before and after the interaction. Like, so the direction is conserved as well. And we'll definitely touch on this, but like, yeah. Momentum before and after has to be the same if momentum is conserved. So, start with a simple example. Everybody good with the right? And the ball's moving to the right, the pin's not moving, the total momentum of the system is to the right. So both objects are part of your system. Afterwards is the total momentum of the system still to the right. Okay? I'm just trying to come up with a really simple example to demonstrate this. Are you okay with that? Okay? Total momentum of the system before and after the collision is going to be the same to the right.
It's not always.
I mean, sometimes it can be the left, but yeah, like the total momentum of the system, yes, will be consistent. Okay, super simple example. We'll get into more complex here momentarily, but like that's the basic framework. Okay. Another new.
To the left. Let's be to the right.
What do you say?
And
Correct answer is A. Okay. You guys remember the bar charts with energy? Fondly, right? So this is a similar type of a tool, but because momentum is a vector, has direction, I've created something different momentum vector diagrams. Has some similarities to the bar charts, but definitely some differences. Okay, so initially, we've got 20 to the right plus 0. The total momentum of the system is 20 to the right. If we put both objects in our system, then momentum is conserved. Afterwards, we still have 20 to the right. Okay. So, working backwards, I've got 15 to the right plus something gives me 20 to the right. That's something, well, is 5 to the right. Okay with that? Did I sound that right? Well, yeah, okay. So I know this is a super easy example, but I'm just trying to show you how to use this tool. Does that make sense? I mean, this is what your homework's going to look like. Good? Tell your neighbor. Correct answer is?
B.
Correct answer is B. Okay. So we've got 140 to the right, we have 200 to the left. Add those together, both are part of the system. You have 60 to the left. We're going to say that momentum is conserved in that collision. So you have 60 also to the left. Now, I want to address something. When I was in your shoes, I had a problem with this. Like, how can you say momentum is conserved? I mean, like, the guys are pushing off the ground. Like, there's friction. There's external forces that aren't canceled out. Okay. Here's the argument for conservation of momentum. During the moments of impact, the force that happens at impact is so much greater than the other forces like friction and stuff that we can say during the moments of impact that momentum is conserved because this force of impact dwarfs all the other forces. It's so much bigger that during those moments we can approximate that to be conserved. And this is what they do for crash scenes. Like when they're reconstructing, they're considering momentum to be conserved even though there was skidding going, like, okay? There's definitely external forces, but the moments of impact, the force from the impact is so much bigger then all other forces that you can say during those during those moments that momentum is conserved. You okay with that? So that's kind of the story behind that. Okay. All right, so demo for you. And a medicine ball. So the system is me, medicine ball, card. Okay? I'm going to throw the ball as hard as I can that way. Okay? So initially, we're all at rest. Okay? Throw it. Okay, let's pretend there wasn't friction. Are we good with that scenario? Okay. Thumbs up when you have a guess. Tell your neighbor what you think. What do you say? Okay, so you're saying there was, how can you say there wasn't any momentum at the end? I mean, like, did the ball have momentum at the end? Going that way? After I threw it? I had momentum, right? I was moving. Wasn't very fast, but I was moving, right? How can you say the total momentum of the system is still zero? Not, I mean, yes, but.
Because the momentum was the same in opposite directions.
Okay, direction matters. Okay? The momentum that the ball had was equal to the momentum that I had. Now, I was moving slower because I had less mass. You okay with that? Okay? So, correct answer is D. Both B and C both experienced the ball and me both experienced the same force for the same amount of time. Therefore, we both had the same change in momentum. Because we both started at rest, we now have the same final momentums, just in opposite directions. So the total momentum of the system is still zero. Okay, so The momentum vector diagram for this one would be starts at 0, total momentum of the system is 0, momentum is conserved. Afterwards, I'm making this up, let's say I add 25 or 20, it doesn't matter. And the ball had to also have 20, so 20 to the left plus 20 to the right still gives you 0. Good? I would recommend doing a momentum vector diagram on this one. Neighbor? Correct answer is? 2 B's. Head nods. Yep. Okay, so this kind of undefined, but the total momentum of the system initially is 40 going up. The explosion was an internal force.
Basically, the explosive holds.
Hmm? So afterwards, you had 50 going up. 50 plus something has to give you 40 going up. Something has to be 10 down. So that's working. Yep. This next question, highly recommend doing a momentum vector diagram. Comes up when you have something. People around you, what you thought. What do we say?
B.
Why? Let's see. Here we go. Ready? We're gonna learn some stuff. Okay. 1 to the right plus 0 gives us 1 to the right. Momentum is conserved if we put both the golf ball and the bowling ball in our system. Now,
That is extremely fast.
the golf ball bounces backwards. How fast? We don't know. But it's not going to be more than 1. Does that make sense? It's not going to be like, whoa, that would be weird. Okay? So it's probably going to be, like, ideally it'd be like 1. Like a perfect bounce. But reality is it's going to be slower, like, it's going to be less than that. Is that okay with that approximation? Okay. So let's just say like 0.8. It could be 0.5, it could be, it doesn't really matter. Okay? To the left. 0.8 to the left plus something has to give you 1 to the right.
Where did you get that point from?
I just made it up, but it's something less than 1. It's bouncing back slower than it came in at.
I don't know how to solve it. Yeah, D.
Okay, but regardless of what you make this plus something has to give you 1 to the right. That something is what? Has to be 1.8 to the right. Correct answer is C. Definitely right. Correct. It is not intuitive. Okay?
It's counterintuitive.
Correct. So, here's how you make sense of this. Direction matters. Direction is conserved. Okay? The total momentum is to the right. You've got something going to the left. In order for the total momentum to be to the right, whatever is moving to the right has to have enough to compensate for the momentum going to the left to make the total momentum of the system still to the right.
So we always try to make the momentum for the final one the same as the initial, right?
That's-
If it's conserved.
If it's conserved, yes.
Okay.
That's what we're going for. So, now, here's a mental splinter that, like, if I was in your shoes, I'd be like, well, okay. You've got gravity acting on the golf ball that's not accounted for. Like, isn't that an unbalanced external force? Do you remember when we were talking about projectile motion, and we said that the forces and the motion in the horizontal direction are independent of the forces and the motion in the vertical direction? Okay, and we've had that theme go along, but it's still valid, okay? So we're just gonna look at the momentum in the horizontal direction. Momentum in the horizontal direction would be conserved legitimately. In the vertical direction, it wouldn't. We're just gonna consider the horizontal case. All right with that?
If something collides, will it always be conserved?
If you put both objects in your system, yes. Okay, good with that? Or explodes. Skadoosh. Okay, I like the rocket ship. Good with that? Okay, so this is what your homework's gonna feel like. Make sure you do the momentum vector diagram. I wanna circle back to Newton's third law. We kind of got robbed of time. So you do have a worksheet that's due tomorrow. I'm gonna go back to lesson 1. Newton's third law. Have a conversation.
Your thoughts on what?
Okay. Funny commentary on this question. I've asked this question. I made this question up like 20 years ago. Every year it's like, see, it's like, okay. So, which object experiences more force, the bullet or the gun?
They're the same.
Same.
Same. Newton's third law. So why does the bullet go flying? Because it has less mass.
But the recoil is what helps.
Right. So there's a kickback on the gun.
Called the recoil.
Okay. Yes, called the recoil. But why? So what would happen if you had a really lightweight gun
You would go yeet.
and you got two bullets? Freeze over. Like you're both dead.
It's not gonna go at Mach 90.
Does that make sense?
It's gonna go at 8 Mach second.
Okay. Yeah. Okay. Hopefully you've already figured out this theme, like the same force, Newton's third law. So let's talk about why something breaks. Why does the bug get smashed and the van just keeps driving from the worksheet? Remember that? Okay, it experiences the same force. So the board experiences force from the hand, the same amount of force that the hand experiences a force back from the board. Okay? The reason the board breaks is because the molecular bonds in the board itself can't withstand that force, and that's why it breaks. The bug died, and the van just kept driving because the bug couldn't handle the force where the van could. You're at that. Okay. Last question. Have a conversation. Why you think?
No, I know.
Will be more.
She also mentioned that.
So,
All right. What do you say? Well, let me talk you through it. So, is normal force have the same magnitude as force of gravity? Yes. Are they acting in opposite directions? Yes. Seems pretty likely, right? This is normal force on the book from the what? From the table. The reaction force, Newton's third law, says it has to be on a different object. So there's a normal force on the table from the book. That would be Newton's third law up here. This and that. Not this and this. This is acting on the same object. These two forces are canceling each other out. This is not Newton's third law. This is false. Okay? What's acting? There's a force of gravity on the book from the what? Earth. Newton's third law says there's a force of gravity on the earth from the book. That would be Newton's third law. Okay? You have to swap objects. It has to be two objects. Object A, object B. Okay? Force on book from table, force on table from book. Force on book from earth, force on earth from book. Has to be flip-flopped. Good with that? Okay. Worksheet due tomorrow. I'll post that